So, hi everyone. Today I'm going to be talking about the solid principles, which are originally a set of design principles created for object-oriented programming. We'll discuss whether these principles are useful in the functional world and see if they can be applied to Elixir, or whether functional languages need a set of their own design principles. My name's Georgina, and I'm a software developer. Most of my professional background's actually been in Java, but at the moment I'm working on a project which is a microservice architecture, and some of the services are written in Elixir. When I first started out my career, I was doing C++ and Java, so probably the most object-oriented languages you can find. And there was a lot to learn. I had to understand how to model the world as objects, not something that I'd done before. I had to learn the syntax of the language so I could bring the solutions to life. And at the early stage of my career, all my effort was spent in lashing some code together and hoping it would work. Over time, I got to grips with the OO way of thinking, and I soon realized that just getting some code to work wasn't really enough, and I needed to take my code to the next level to make a more robust and a more testable, long-lived project. So luckily I made a career move and I joined a consultancy which was very much focused on clean coding practices, and the solid principles were an integral part of the developer process. After applying these principles to my Java code, it enhanced my code in such a way that I had a more maintainable and long-lived product. The same company asked me to learn a functional language, so as a consultant I could go into various clients and be able to evaluate what languages and paradigms were best suited to the problems that they were facing. And I chose to learn Elixir. Before learning Elixir, I had years of experience of problem solving and system analysis, so I had to learn the syntax. But the syntax is quite nice, it's quite approachable, so I didn't find that too much of a barrier. So I quickly got something working. And then I found I was in the same position as I had been earlier in my career. I wasn't sure how to take my Elixir code to the next level in terms of design. I wasn't aware of any functional specific programming design principles, so I decided to do an experiment and apply the solid principles to my Elixir code. The solid principles are 5 design principles where each letter is an acronym for a given principle. When applied, they're intended to improve the quality of the design of your system, so you've got better maintenance, reusability, more robustness, and you avoid making breaking changes every time you need to face adding new functionality. So they're originally devised for OO languages, but I wanted to see if they could be applied to a functional code base. The use case that I've decided upon for today's talk is an Elixir microservice which forms part of a holiday booking system. The code we'll be looking at is concerning customer search preferences, and it's a web plug project, so services communicate using HTTP. The booking site has many forms like so, where customers can select their holiday accommodation preferences. They press search, and they'll be presented with various accommodation options. The first time you log onto the website, there'd be no options pre-selected, but every time you search for some accommodation, it would save your preferences to an underlying database, so that the form is pre-populated next time you log in. So in order to fetch the pre-saved preferences, we have a GET endpoint in our system. A typical workflow is that a customer logs into the site and navigates to the search page. When the form is loaded, it will call the GET endpoint of our plug system. Under the hood, the database is queried using the customer ID, which is obtained from the login. And we're using DynamoDB, which is a database offered within the AWS stack. A matching record is found, and that record is stored in an internal map structure. We do some transformation so that we return JSON back to the calling client. Having explained how to fetch the saved preferences, we also have to add new preferences, and for that we have a post endpoint. For the post use case, the user logs in, navigates to the form. They choose the selections that they want to search for, and they press the search button, and that invokes the post endpoint. This time we receive JSON. We have to transform it into a map so that we can then go ahead and save it in our database. So for the purposes of this talk, just think about this service as a glorified CRUD system. So now that we have a flavor of the domain, we can go back to our solid principles. The first principle is single responsibility. So this is the official definition of single responsibility on Wikipedia. It states that every module or class in your system should be responsible for a specific part of your system. So what does that mean? Well, using this definition, let's decide on this occasion that getting user preferences is a single part of our system. It's a single use case we need to implement. So let's see if we can write a module that fulfills that single responsibility. So here's our web controller, which is responsible for fetching the user preferences. And as described in the use case, it will go ahead and query the Dynamo database to see if it can find a record for the given customer ID. We have to decode that database response because DynamoDB saves some metadata along with the actual business data, and we want to strip that out by transforming it into an Elixir struct. And then we transform our database row into some JSON, which we return back to the calling client. So in a nutshell, we broadly have three things going on, three different steps happening in our controller. We query the database to look for a matching record. We decode the database data to strip out excess metadata that we don't need. And then we format that data into JSON so it's a bit more human readable for the calling client. So is this single responsibility? Together, those three steps do make up the single use case for fetching user preferences. But let's ask ourselves a question. So one way to identify if you're violating the single responsibility principle is to ask yourself, of the steps that are happening in this module, can any of them change independently? For instance, if we decided to update our query to the database so that rather than just providing a customer ID, we also provided a geographical region, would the other steps in our controller need to change? Possibly not. And in this case, it wouldn't, because if the data coming back from the database doesn't change, our transformation to JSON won't change either. So this could indicate a violation of the definition that we gave earlier, because we've identified distinct steps that can evolve independently. For reference, there's always lots of interpretations of these principles, and so I tend to favor this one from Robert Martin, who's a big advocate for clean code and architecture in the OO world, and he states that a class should only have one reason to change. Now in Elixir, we don't have classes, rather modules, so we could update this definition to be, for Elixir, a module or even a function should only have one reason to change. So at the moment, we have three steps inside one module. Let's apply this new definition of single responsibility to see if the solution suits having a different module for each step. So first of all, let's extract out the database lookup. We can already see at a glance that this is now a much more concise and smaller module, and it can be tested independently and tested in a much more focused manner. Now, if we needed to change our JSON transformation, for example, we wouldn't even need to open up this module and look at it because it's completely isolated. The next step was decoding our database data into a struct. Now, it's debatable whether this actually warrants its own module, because if we look closely at this code, it's really just wrapping a library call, and there's not really any business logic going on here. So we should make sure that the modules we break down do warrant their existence, and this may be better suited merged with the previous module that's looking up the data with the database. And the last step was transforming the JSON, and it makes sense to extract this out because really it is doing a completely different job. It's not interacting with the database at all. Our calling code, our controller, now becomes much simpler. It just coordinates the calls between the new modules. And so we need less tests at this level now. So if we think back to when we had everything inside one module, if we wanted to test the JSON transformation, we'd have to mimic hitting the get endpoint. We'd have to mimic hitting the database and a row coming back from the database. We'd have to decode that data, and only then would we be able to see if the JSON had been transformed correctly. Whereas having separate modules, we can now test those things directly, and we can have much more focused tests. And focused tests tend to lead to much more focused failures. And focused failures tend to lead to quicker resolutions because it pinpoints exactly where the problem's happening. And our higher level tests can become a thinner suite, and they're typically more expensive to set up and run anyway. Of course, there's always trade-offs, and every module does need to earn its right to live. There's an overhead with every module that exists in terms of maintenance and testing. So it's a good idea to evaluate how you've split up your system. And if you end up with a plethora of tiny modules, of which some always change together, it might be a sign that those modules should actually be merged together and should live together. The next design principle is called the open-close principle. So this principle states that you should be able to add new functionality without changing functionality. And this sounds very much a contradiction. So I like to summarize it as the ability to add new code without touching any existing source code. So as a quick reminder, we have our post endpoint to save search preferences to the database. So that we don't save any incomplete data, we want to perform some validation on the payload that we receive. We want to check, is the customer ID that they provided a valid customer ID? And we want to make sure that there are certain mandatory fields present in the payload. With single responsibility in mind, we could model each validation rule in a separate module. We can go ahead and execute those rules. If they all evaluate to true, we can persist the customer's data to the database. And if there's any errors, we want to handle those errors, provide a reason, and send that back to the client. So we want to add a new validation rule. Easy. We add a new module with the business rule inside of it. We can update our with statement. And we can update our error handling so that if that rule fails, we can give a reason and send it back. But wait a minute, the open-close principle says that we shouldn't be touching any existing code when we're adding new functionality. And if we do what I just said, we would be modifying existing source code, which is against our rule. So whilst this is a trivial example, production large systems are often have lots more complexity. And as you add more and more rules, your system becomes much more difficult to test. You might have lots of permutations that you need to test. So it might be better if we have the ability to plug rules in and out. Then in our, say, unit test environments, we can just plug in 1 or 2 rules for unit testing. But in our production environment, we can plug in all 5, 10, 100 rules that we have in our system. So let's try and configure a plugin architecture. So looking at the original set of rules, they tend to fall into 2 categories. There's those that concern the header properties, and there's those that concern the payload, the body of the request. So instead of having them all listed in this with statement, we could model it slightly differently. We could create a list of the functions for the header validation, and a list of functions for the payload validation. We could then wrap those lists in another module, and that module could iterate through those rules and execute them one by one. And then if there's any errors, we can fall out of the loop. For example, here we have our header validation functions configured in a list, and we can recurse through that list and fall out if there's an error. So now, if we were to add a new rule, we would just need to add it to our list. And the code surrounding that list wouldn't actually need to change. This simplifies the calling code. So the with statement would just call the wrapper modules, and it would just need to check all the header rules and all the body rules. The details of the rules that we're actually executing is now hidden from this level. So if we add another 10 rules, this module doesn't need to change. So this module is now adhering to the open-close principle. So what would we need to change now if we were to add some new validation rules? Well, we would need to configure a new module with our rule in it and add it to our list. And if we think of this list as configuration rather than code, we could tell ourselves that we are adhering to the open-close principle. But there are trade-offs with this, of course. Testing hasn't become any easier. If we have 100 rules, they're still going to be listed in this list, and we still need to unit test all the permutations. So we've definitely made a step in the right direction by isolating our area of change to a single list. But another thing to think about here is there's no guarantee as to what these rules are going to return. And we don't really know what parameter we need to pass in. And with Elixir being so flexible, you can pass in any function here. But our surrounding code is expecting the return values to be in a certain tuple format. So we could use an Elixir behavior to try and put a bit of a contract in place. And that will enforce a contract between the rules. Each module that's going to adhere to this behavior would need to provide implementation details for the functions that are defined on the behavior. And if you're familiar with Java, you can think of a behavior as being similar to a Java interface. So we could define a behavior something like this, which is saying that any module that uses this behavior will need to provide an implementation for the isValid function. And this function would need to return a tuple of either OK or an error with some reason. So now we have to update all our validation rules so it actually adheres to this behavior. And to do that, we can just provide the annotation to use the behavior, and then we'd need to provide the body of the isValid function. This way, rather than configuring a list of functions, we can actually just configure a list of modules. And then when we're iterating through these modules, we can call the isValid function directly because it's now guaranteed that these rules actually adhere to this contract. And the last step would be to make this list of modules fully configurable, and we could do that by moving them into the Elixir config. And this way, we can configure different rules for different mix environments. And then at runtime, we can look them up using the application getenv. And this way, we've achieved being able to configure 1 or 2 rules for our unit testing, but we can configure however many rules we want for production. So now, if we add a new rule, we need to add a new module containing that new rule. And we need to add it to our list of our module names in our config. So we're finally adhering to the open-close principle because we can add new functionality without touching any existing code. Again, this may seem overkill for this example, but if you're working with a large complex system and you need the ability to plug in and out features, or you've got rapidly changing requirements, being able to have this plug-in architecture can be quite beneficial. The next principle is called Liskov substitution. Now, in object-oriented programming, you have classes, and classes can inherit behavior of other classes. So in this example here, we have a base class called report, which has a format method, and we have a subclass called marketing report, which inherits this format capability and then has some methods of its own as well. Okay, so I wouldn't even try and understand this definition if you've not seen it before, because it's like a foreign language. But what it's trying to say is that we should be able to substitute any of the subclass type with that of the base class type. And this is probably best described using a small code snippet. So this is a snippet of Java code. So avert your eyes if you don't like looking at Java code. This is just creating a new marketing report and calling the method format. The Liskov substitution principle is saying we should be able to change the type of marketing report to the base class of report without any undesirable effects happening in the system. So it should still compile and run. And this works because of our inheritance model and the format method being available at the most generic level there is. Now, in functional programming, we don't tend to use inheritance as much. sometimes not at all. But let's see one way that we can mimic something similar using Elixir. So we have some reporting capabilities in our holiday service. User preferences are sent to various departments, so we send our preferences to the advertising department so that targeted marketing adverts can be sent to you. Additionally, data is sent to data warehouse so that we can build up a historical store of all your preferences, and we can look for things like trends. So in a nutshell, the data that's persisted is sliced and diced, and different views of that data are sent to make the different reports. So to help model this, we'll use another behavior. Each module that implements this behavior will provide its own bespoke implementation of how it wants to format the data for the report that it's responsible for. So we can map different modules to different parts of this diagram. For example, we have our advertising report, and that uses the formatter. And inside the format to rows function here, it will format the data as is needed for the advertising report. We have a historical data report for data warehouse. And again, that uses the same behavior, and it will format the data differently as it needs for this data warehouse report. And then we have a report generator, which will format the data and dispatch it and do all that coordination. So that takes the raw database data and a list of different formats, and it will loop through and generate the different formats before dispatching. So here, we could actually plug in any formatter, any module that uses the formatter behavior, and we'd be able to successfully format our report. So we could say that this is adhering to Liskov substitution. There'd be no undesirable effect if we put in a new formatter. That's great. But our holiday site's really taking off, and there's a new regulatory requirement that comes in, and suddenly we need to generate a new report for legal. And legal's always a bit difficult. They're never happy with something you already have. So although we want to use the same format as the data warehouse, they of course want some extra information. They need a disclaimer and a header. They want some colors. So there's some extra work that we need to do. So we could write a new legal report generator. This takes the database data and a formatter. It will format the rows as it has done previously, but it also will go on to add the disclaimer and add the headers and add the colors before dispatching. Now, we already have a module that formats the data as we want, so we already have our format to rows function there. But let's go ahead and add our new functions. So we add our disclaimer and our header and so on. So now when we pass in our historical data format to our legal report generator, everything works great. It generates it as we wish because it has a definition for all of the functions that it's expecting. But what happens now if we pass one of the other formatters into the legal report generator? Let's take the advertising report, for example. It implements the formatter behavior, but that only has the format to rows function defined on it. So the first step would be successful. But when it comes to adding the disclaimer and the header, we haven't got an implementation for them available on this formatter. So of course, we would get an exception. We'd get an undesirable effect. So we would be violating the Liskov substitution principle. Because according to that, we should be able to plug in any formatter and everything works as expected. So we need to think a bit more. We know we want to format the data as an existing formatter, but we know we need to do something extra. So rather than updating the existing historical report, we could try creating a new report which uses the existing one so that we reuse the formatting capability, and then we can add the extra details in the new module. So we created a new module and used the same behavior so we don't break any contracts. In the format to rows function, we can delegate our formatting behavior to one of our existing reports so that we reuse that capability. And then we can go on and add the new presentation layer functions. So now we've actually been able to hide this extra presentation behind the actual behavior that we have. So all of our reports now adhere to the same interface, essentially, and we can just use the same report generator. So by wrapping an existing report, we've been able to extend its functionality without exposing that detail to the outside world. And now we can substitute any of those different formatters safely. So perhaps in Elixir, we could think about the Liskov substitution principle as follows. Where we have code that expects a behavior type, we should ensure that we're only using functions that are defined at that most generic level. So that works fine. But why didn't we just update the formatter in the first place? And then we could have updated all of the reports to provide a disclaimer and a header and the colors. Well, we saw how this would potentially make sense for our data warehouse report, our historical data. But it doesn't really make sense for our advertising report because it doesn't need these extra presentation functions. But if we had updated the formatter, we would need to provide an implementation for these new functions to fulfill the contract. So in our advertising report, we would have had to have provided an add disclaimer function, an add headers function, but the detail would have essentially been empty. There'd be no business logic we need to do because these functions would be redundant. And this is confusing for people working on the code base because if you see a behavior defined with different functions on it, you think that they're important and you think that you need to provide good implementation for them. And if you just provide an empty implementation, it's usually a sign that your design isn't quite right. And similarly, if we have lots and lots of different reports, we don't want to have to update them all just because one or two of them need these extra presentation functions. So if we had done this, we could say that we'd bloated the behavior in order to satisfy a new requirement. And this would actually be violating the next solid principle, which is interface segregation. So the interface segregation principle states that clients should not be forced to depend on contracts that they do not actually use. In object-oriented programming languages, there's various signs that you can look for to see that this principle is being violated. Typically, you see it in very tall class hierarchies or interfaces or classes that have lots and lots of methods split over different responsibilities. And translating this into the world of Elixir, we could look for large behaviors or modules with lots of functions, again, spread out over lots of different responsibilities. So we've already discussed that adding all of these new functions to the original behavior is not a very good idea because it's not relevant to all of the different reports. So let's leave the original formatter behavior as it was so we don't break the advertising report. And instead, let's create a second behavior that is around presentation and has those presentation functions on it. So the historical data report can now be updated to implement both behaviors because Elixir lets you use as many as you like as long as you provide the detail for each of the functions defined. And this way, when we generate our report, we can split it up into processing the formatting of the data, then presenting the data, and our calling code can decide which reports are needed to run through which step. So this way, we've kept the necessary functionality restricted to the modules that actually need them. And you'll find that several of the solid principles start to intermingle because by making sure your behaviors are focused, you're usually enforcing the single responsibility principle as well. So that brings us to our last solid principle, and that's dependency inversion. And unfortunately, that isn't me in the picture, by the way. Now, there's too many words on Wikipedia to put the whole definition, but I've tried to extract the essence of it here. And dependency inversion is around separating your high-level layers and your low-level layers. So looking back to our get endpoint, we have the ability to fetch data, customer data, from the database. And the database is an external dependency. If we look at our implementation, we're using a library to look up and interact with our DynamoDB. Using this library, we have a couple of options to configure to different databases. We can configure to point at a real DynamoDB table in a real instance of AWS, Or you can run a Java process which will bring up a local DynamoDB, and you can connect your Elixir code base to your local instance. But either way, you need to have an external database running in order to connect to it. And when I'm running my unit tests, I don't want to connect to a real AWS instance. And I don't want the overhead of having to orchestrate bringing up a local DynamoDB so I can hit it and clean it out and all that overhead. So to adhere to dependency inversion, I want to start splitting this up. I don't want my high-level module, which is get customer preferences in this case, to depend or be tightly tied to this library, which is expecting a real database to exist. I want to provide an abstraction in between such that I'll be able to provide a fake database so that when I run my unit tests, I don't need to bring up any real database at all. And then I can configure on different environments, different implementation details for the database. So in my test environment, I can use my fake one, and then in production, I can use my real one. And if we look at the code base closely in the library, there's actually only one line that actually physically connects to the database. So if I can isolate this one line, I have more control as to whether I use that original line from the library or whether I substitute in my fake call. And Elixir gives you a couple of ways that you can do this. One method of decoupling that we can demonstrate the dependency inversion principle with is to use ElixirConf to substitute different implementations for your different mix environments. So as per dependency inversion, let's modify our design slightly. We can provide different implementations of a database, so we can have a real AWS request database and our fake database. They can depend on an abstraction, and in Elixir we can use a behavior for this abstraction. Then we've got our high-level module, get customer preferences, and if we let this depend on the abstraction as well, we've created a layer between our high-level modules and our low-level modules. This way we can change our database implementations without the high-level module knowing, so it's completely separated from the details. So first of all, we create our abstraction, which in our case will be our behavior. And that's the layer between the high-level modules and the low-level modules. We can wrap our real database functionality behind this abstraction. So we again use that behavior, and we have that call that hits the real database. And then we provide a fake database. This will also use the same behavior, but it will just return a canned result, and it's a hard-coded result in the same format as what would come back from the real database. So now we can configure which one to use in which mixed environment. So when I'm running my unit tests, I can just get that canned result coming back every time, but in my other environments, I can use the real AWS instance. So we can utilize Elixir's config again to configure what implementation we want for the different mixed environments, and look up again at runtime which one we should substitute in. So it seems that we've achieved what we set out to here. We're not dependent on the details of our database implementation anymore, and we can configure in and out different ones depending on our needs. But there's always trade-offs. So what happens if I want to test different scenarios? At the moment, my fake module always returns the same hard-coded result. In another test case, I might want to hit the database and mimic no result being found. In another test, I might want to hit the database and mimic an error being raised, or multiple rows being found. And at the moment, we always return the same value. And the only way we could drive logic in our fake is through the parameter that's passed into that function. And in our case, that's the customer ID. So you might end up with some logic in your fake database along the lines of, if customer ID is 1, then return the canned result. If customer ID is 2, raise an error. If customer ID is 3, return empty results, and so on. And it's difficult to keep that expressive through the code. And when you're looking at a test case, it's not always easy to know what branch of that logic would be executed, and which branches are never executed. So maintenance can become a bit of an overhead. And as that complexity builds, do you then need to unit test your fake database? And so it kind of can grow out of control if you're not careful. So in summary, using config files definitely gives you some flexibility, and I've used them quite a lot to plug in and out fake implementations. But if you have a rich set of testing scenarios that you want to cover, it may be difficult to keep that maintainable and expressive through the code base. So another option that I've started using is to use a mocking library. And this way, you can define the behavior of your fakes right there in the test case, which is where it's most relevant. So at a glance, it tends to be clearer for the developer what behavior is going to be returned from the fakes. So to use mocks, you add it as a dependency to your mix file. And we want to keep our dependency inversion design, so we have our abstraction still. But using a mocking library, we don't actually need to physically create our fake database ourselves, so we can cut out that part from the picture. We still need to wrap the real database functionality behind our abstraction. We can configure that in to use in production through the config. And then in our test config, we state that we want to use a mock. And that can be any name that you like, because we're not actually physically going to create it. Instead, we ask mocks to create it for us. So we say, create me a mock request module that implements this behavior. Then in our production code, we can look up at runtime which implementation we want to use. And then in our tests, we can use mocks by importing it, defining an attribute, and then giving the expectation as what we want returned when the database is actually invoked. So here we're saying when the request function is called on our fake, then execute this function and it will return an OK tuple with the canned result. So the main advantage here is that you can define in the place where it's most relevant the behavior that you want your fake to actually run. You don't need to traipse through lots of different modules that are somewhere else in your code base and trying to figure out what behavior will happen. Now, if you forget to provide your expectation, you will get an exception. And I found this quite useful in terms of when I'm writing higher level tests that span through several layers of the application. It really brings it home as to how far through the system your tests are actually going and how many hits to these external systems you're actually making. Because sometimes you forget that you're doing a read and then a write. Or I found that having this feedback is actually really useful to keep my tests more concise. So although there's similarities between using a mocking library or writing your own, a mocking library tends to give you the convenience of being able to define lots of different return values, as well as using a rich set of verification to check that your external systems are hit a given number of times. The only slight untidy edge is that mix gives you a warning because you're referencing a module your fake module, which actually physically doesn't exist in your file tree. But I can live with that. So in Elixir terms, we could suggest that dependency inversion is useful if we depend on abstractions rather than the detail, because it certainly helps you test, particularly when external systems are involved and you don't want to use them in your test environment. So can you write solid Elixir? Well, we just did. We've pretty much applied every one of the solid principles to our Elixir code base. I think the real question is, does it make sense? Does applying these rules make for idiomatic Elixir, or have we just ended up with an Elixir code base that resembles something like Java? Are these the right rules to use in a functional landscape? We need to remember that the characteristics of a functional language are quite different to that of object-oriented languages. Amongst other things, functional languages tend to be about passing data around, whereas in object-oriented, you're reacting to messages that are being sent between objects. So I think the solid principles get you started in Elixir, or functional, but probably we need to tweak the rules to be more aligned with the functional characteristics. With maintainability in mind, it seems sensible that we continue to use the single responsibility principle. Do one thing and do it well. Having small focused functions is as good in Elixir as it is in any language, functional or object-oriented. And functions are the building blocks of our functional languages. So we can think of the single responsibility principle as having small focused functions. And in Elixir, we can compose functionality by passing functions in, returning functions, composing functions together. So having them small and focused will help any potential reuse. So from my point of view, S is fully implementable in Elixir. Regarding open-close, it seems sensible and low risk that in adding new functionality, we don't touch any existing code. This reduces any retesting effort, and it makes the code and the tests more focused. In Elixir, we have higher order functions, so we can pass any functions in. And in some ways, that makes the open-close principle very easy because we can just pass new functionality in without touching the body of the function we're passing it into. Bearing in mind, with great flexibility can come a great mess. So you may need to think about if you need to put in any contracts like what we did with the Elixir behaviors. So I think open-close is a good goal to strive for in functional programming. So what about Liskov substitution? In OO, this tends to hinge off inheritance. And I haven't tended to use inheritance very much at all in functional programming. So perhaps this one we need to redefine. And one of the things that functional programmers strive for is purity. A pure function has an input and an output. Given that input, you will always get the same output. There'll be no side effects and no state modified. So let's imagine this pure function, which simply adds two numbers together. Given another function which uses this, which is also pure, we can calculate its output. So the output of our lucky number function would come out at 7 every single time. So if we substituted the number 7, every occurrence where we're calling lucky number, there should be no undesirable effects in our program. The result of the evaluating expression is going to have the same mathematical value as the starting code. And this is known as referential transparency. So I would propose that we modify the definition of Liskov substitution, and instead we use referential transparency, thus replacing the L of solid with RT. In OO, interface segregation is about keeping your interfaces small and focused, only forcing contracts where necessary. In our case study, we saw how the Elixir behavior could help with this. And in the Elixir source code, documentation, it actually says, if you have to, you can think of an Elixir behavior as being similar to a Java interface. So I think this supports my conclusion that interface segregation should be applied to the Elixir behaviors. And we showed how by creating an abstraction, we can decouple various modules in our application, and that this resulted in a code base which was more flexible and easier to test without depending on external dependencies. So we created an abstraction between our database and our high-level modules, and we could then substitute in different implementations. So particularly with testing in mind, I think having a principle such that we can depend on abstractions rather than concrete implementations makes a lot of sense. Now, the existing solid principles were created for OO languages, and we need to remember that functional languages have no state, they're immutable. Typically, recursion is used over imperative looping. So I'm leaving you with a question as to whether, at a future date, we need to work some of these traits into our design principles. So coming back to the title of the talk, many of those who consider themselves a functional programmer brush aside the learnings of the OO community. By going to the extreme and forcing these principles on my Elixir code base, at face value, I found a lot of them made sense. I had a lot of code that became smaller, more focused, and easier to test. And regardless of what we consider to be great idiomatic Elixir, I'm sure we can all agree that we need to write code that's maintainable and easy to work with and easy to extend. And we're lucky that Elixir, being a kind of newer language and has learned a lot from existing languages, it already lends itself to being nice to use with immutability, pattern matching, being able to compose functions, having behaviors and protocols all built in. So we concluded that S for single responsibility was applicable for functional languages. I suggested that open-close was a good goal to strive for. We discussed that Liskov substitution should be replaced with referential transparency to acknowledge the purity of the language. Using behaviors, we can adhere to the interface segregation principle, which leaves D for dependency inversion, in which case the baseline for design principles in Elixir could be sorted. Thank you very much.